Welcome back, everyone, to Restly, where we settle into the science of deep cosmic rest and the profound sleep of the universe. Today, we are not focusing on sleep itself, but on one of the most violent yet profoundly final events that happens after the life of stars has ended. The true collision of two of the universe's greatest gravitational behemoths, black holes. To comprehend the impact and scale of such a merger, we must first settle into the background, understanding the deep cosmic history and meticulous orbital dynamics that bring two such titans to their inevitable, explosive union. This journey begins with the formation of a binary system, the nature of space-time itself, and the billion-year process of orbital decay known as the inspiral. A black hole, as you may know, is the ultimate gravitational collapse of a truly massive star. When a star with an initial mass exceeding approximately 25 times that of our Sun exhausts its nuclear fuel, its core can no longer withstand the immense force of its own gravity. The core collapses inward in a spectacular cataclysmic explosion known as a supernova. If the remaining core is sufficiently massive, it is crushed down to an infinitely dense point called a singularity, surrounded by a boundary of no return, the event horizon. This object, the black hole, represents the greatest concentration of mass in the universe, warping the very fabric of space-time around it. It is a well-established astronomical fact that most stars in the cosmos are not solitary like our Sun. They are born and exist in pairs or larger multiple star systems, orbiting one another in a gravitational dance. When two incredibly massive stars, each potentially 30 to 50 times the mass of the Sun, are born close enough together to maintain a stable, tight orbit, and both proceed through their entire life cycle, they are destined to become a binary black hole system. The more massive star evolves faster, collapsing first into the initial black hole. The companion star continues its existence, orbiting its now dark partner, until it too runs out of fuel, collapses in its own supernova, and forms the second black hole. What is left is a compact two-body system, two enormous spheres of pure gravity circling a common center of mass in the vast, deep emptiness of space. The general theory of relativity, developed by Albert Einstein, provides the essential physical framework for understanding the relentless fate of this binary pair. According to this theory, space-time is not merely an empty void, but an active, flexible, four-dimensional fabric, like an enormous, taut rubber sheet. Any object with mass creates a dip or a well in this sheet, and the motion of objects is dictated by this curvature. This is what we call gravity. When two objects as intensely massive and dense as black holes are in rapid orbit, their extreme motion and mass create continuous, powerful disturbances in that sheet. These distortions propagate outward as gravitational waves, ripples in the curvature of space-time that travel at the speed of light. The emission of these gravitational waves is the single mechanism that guarantees the eventual collision. The key principle, derived directly from Einstein's theory, is that the emission of these ripples carries away energy and angular momentum from the orbiting system. This loss of energy must be balanced, and the only way a gravitationally bound system can maintain its equilibrium while losing energy is by reducing the distance between the two bodies. This slow, steady reduction in orbital separation is the inspiral, the gravitational wave death spiral. In the earliest stages of the inspiral, When the black holes are separated by distances comparable to the size of a typical solar system or more, this process is glacially slow. The gravitational waves emitted are relatively weak, and the orbit shrinks by only a minuscule amount over vast cosmic timescales. They may orbit for billions upon billions of years, a period that would make the entire age of our universe seem short. This is the period of deep, slow cosmic rest for the early binary system. However, the dynamics change dramatically as the orbit slowly contracts, as the distance between the black holes shrinks from light years down to light hours and then to light minutes. The mutual gravitational pull intensifies, and the velocity of the black holes increases exponentially. The power radiated in gravitational waves is not linearly related to the orbital parameters. It increases drastically as the separation decreases. This non-linear effect transforms the ancient waltz into a frantic terminal sprint. In the final millions of years, the two black holes are rapidly rushing toward each other. The rate at which the orbit shrinks accelerates, moving from perhaps a few centimeters per year to many kilometers per second. During this crucial inspiral phase, the orbital period, the time it takes for them to complete one circle, drops from weeks or days to mere seconds. In the final hour before collision, the black holes might complete thousands of orbits, each one closer and faster than the last. Their velocity is now an appreciable fraction of the speed of light. The crescendo of this gravitational wave emission builds relentlessly, extracting colossal amounts of energy from the system as it heads toward its lowest possible energy state. The final stage of the inspiral is defined by extreme relativity. The two event horizons are within touching distance, separated by only a few hundred kilometers. The intense gravity of each object profoundly distorts the space-time around the other, pulling their event horizons into extreme, elongated shapes. They are moving at enormous speeds, ready to plunge into one another. This relentless, accelerating decay, powered entirely by the emission of space-time ripples, is the defining fact of the binary's existence, setting the clock toward the violent final collision that is now just milliseconds away. The cosmic sleep of the system is violently broken by this final terminal motion. The billion-year cosmic inspiral has concluded its slow prelude and now plunges into its terminal climax. We are now in the terrifying final milliseconds, the relativistic dance, where the black holes achieve a tremendous velocity, leading to the instant of maximum energy release and the profound physical event of the true collision of the event horizons. This phase is entirely non-Newtonian, governed by the deepest and most extreme consequences of Einstein's general theory of relativity. In the final seconds of their orbital existence, the two black holes are traveling at a substantial fraction of the speed of light. If they are both around 30 times the mass of the Sun, they are orbiting each other at a distance of only a few tens of kilometers. The orbital period has compressed from years to mere milliseconds, meaning they are whipping around each other hundreds of times every second. The extreme velocity and proximity create an incredible, complex distortion of space-time around them. The gravitational field is so intense that time is heavily distorted, and the light paths are wildly bent, creating a scene of physics pushed to its ultimate limits. It is during this hyper-accelerated phase that the gravitational wave emission reaches its ultimate towering peak. The rapid increase in the orbital frequency and velocity causes a dramatic spike in the amplitude and power of the outgoing space-time ripples, producing the characteristic cosmic chirp signal. This phase is characterized by the maximum energy release of the entire event. Consider the astonishing fact: for a fleeting fraction of a second before the event horizons merge, the power output of gravitational waves can briefly exceed the total light output of every star in the entire observable universe combined. This enormous momentary power output is the final, greatest act of energy generation in the system, a pure, silent surge of gravitational energy extracted from the colossal orbital kinetic energy and the immense gravitational potential energy locked between the two objects. This maximum energy release is the reason these events are detectable across billions of light-years of space, serving as the universe's loudest non-electromagnetic announcement. The climax of this relativistic dance is the true collision, the moment the two separate boundaries of space-time, the event horizons, touch and coalesce. We must recall that a black hole is fundamentally defined by its event horizon, the boundary from which light cannot escape. As the two black holes whirl at near the speed of light, their extreme gravity deforms the shape of the other's event horizon, stretching and pinching it due to intense tidal forces. The event horizons are no longer perfect spheres. They are violently warped structures. The collision happens at the instant these two boundaries make contact and begin to overlap. At this microsecond in time, a single, common, and incredibly distorted event horizon forms, wrapping around both of the original singularities. The entire topology of spacetime in that immediate region changes irreversibly from a two-hole structure to a single, chaotic, merged structure. This is the moment the two separate black holes lose their individual identities and are reborn as a single unified entity. Inside this new, single, larger event horizon are the two original singularities, the points of infinite density. They continue their rapid internal motion for a brief period before finally coalescing into a single, even more massive singularity at the core of the new black hole. However, the observable gravitational event of the collision is the merging of the horizons. The newly formed event horizon is immediately in a state of maximum instability. It is highly irregular, often visualized as a spinning, violently wobbling and elongated shape, similar to a droplet of liquid that has just absorbed another. This extreme asymmetry is the final source of the rapidly decaying burst of gravitational waves that will follow, a phase known as the ring-down. The physics of this instant confirms the profound link between mass and energy as established by Einstein's famous equation, the formula where energy equals mass multiplied by the speed of light squared. The total mass of the final black hole is always less than the sum of the masses of the two original objects. That missing mass, which can be equivalent to several times the mass of our Sun, is exactly the energy that was violently liberated in the form of gravitational waves during the inspiral and merger. The collision is, therefore, the greatest single act of mass energy conversion that the universe performs. The extreme relativistic dance and the subsequent merger solidify our understanding of the fundamental nature of gravity at its most intense. The black holes existed for eons, spiraling toward this terminal moment, a perfect demonstration of general relativity where their velocity and extreme proximity ensure the absolute most powerful energy output possible before their unified, enduring slumber begins. The loud chirp that travels across the cosmos is the direct result of this final, most spectacular act of cosmic unification. The catastrophic instant of the collision has passed, leaving behind a single, enormous, and highly turbulent gravitational body. This immediate aftermath is the domain of remnant formation, where the chaotic newborn black hole settles into its identity through a process called ring-down, simultaneously creating a massive mass-energy conversion and potentially imparting a powerful recoil kick that sends it hurtling across the cosmos. The black hole, formed immediately after the two event horizons merge, is violently warped and distorted, far from its theoretically perfect, stable shape. It is an asymmetric, spinning, and intensely vibrating structure. According to the foundational principle of black hole physics, the no-hair theorem, a stable black hole can only be perfectly described by three externally observable classical characteristics: its total mass, its electric charge, and its angular momentum, or spin. All the messy details about its tumultuous formation, the hair, must be radiated away to restore its perfect, smooth geometry. This necessity for structural perfection drives the chaotic, short-lived phase known as the ring-down. The newly formed black hole behaves like a gigantic, cosmic bell that has been struck with maximum force. The impact of the merger sets the entire structure of the event horizon vibrating wildly. These vibrations are not traditional sound waves, but powerful, oscillating disturbances of the surrounding space-time itself. These disturbances propagate outward as the final, rapidly decaying burst of gravitational waves, the last segment of the full chirp signal. The ring-down signal is incredibly distinctive because the new black hole can only vibrate at specific, characteristic frequencies, known as its quasi-normal modes. These modes are uniquely determined only by the final mass and spin of the remnant, serving as a direct and powerful test of the no-hair theorem. If the detected frequencies and their corresponding decay rates match the precise theoretical predictions for a final Kerr black hole, a spinning black hole with that measured mass and spin, then Einstein's theory is confirmed in its most extreme domain. This process is astonishingly fast, lasting only a few milliseconds, a mere blink of an eye, as the new black hole sheds the last vestiges of its chaotic, asymmetrical past. The energy radiated away during the ring-down contributes to the overall colossal mass-energy conversion of the merger. The total mass lost during the entire in-spiral, merger, and ring-down is equivalent to the energy carried away by the gravitational waves. As established by the formula where energy equals mass multiplied by the speed of light squared, the conversion of a vast quantity of mass, often 3 to 5 solar masses, into pure energy is what makes these events the most powerful single acts of mass energy transfer in the universe. This lost mass is precisely the kinetic and potential energy that was holding the binary system in its high-energy orbital configuration. Once the system collapses into its lowest energy state as a single object, that excess energy is shed entirely in the form of space-time ripples. Finally, the asymmetry of the gravitational wave emission leads to the fascinating and dramatic phenomenon known as the recoil kick. If the two initial black holes had unequal masses, or if their individual spins were misaligned relative to the orbital plane, a scenario known as a precessing binary, The release of gravitational waves during the violent merger is not perfectly uniform in all directions. Since gravitational waves carry linear momentum, this uneven emission acts like a powerful cosmic rocket exhaust. To conserve the total momentum of the system, the newly formed remnant black hole receives a powerful kick in the opposite direction to the strongest wave emission. The resulting recoil velocity can be extreme. Theoretical calculations and observational analysis of gravitational wave signals suggest that the final black hole can be launched at incredible speeds, potentially exceeding 5,000 kilometers per second. To provide context, the escape velocity of even the densest globular clusters or galactic cores is only a few hundred to 1,000 kilometers per second. A recoil kick of this magnitude is entirely sufficient to eject the newly formed, heavier black hole completely from its host galaxy or star cluster. This recoil kick has profound implications for the cosmic landscape. If the black hole is ejected, it becomes a rogue celestial body soaring through intergalactic space and unable to participate in future mergers within its own galaxy. This can limit the hierarchical formation of more massive second-generation black holes. The ringdown, the mass-energy conversion, and the recoil kick together represent the immediate, violent aftermath that determines the final mass, spin, and location of the single black hole before it enters its enduring state of final, deep, cosmic rest. The sheer violence and invisible nature of a black hole collision mean that it would remain entirely theoretical without the phenomenon of gravitational waves, the space-time ripples that serve as the universe's only messenger for these dark events. The detection of these waves represents one of the most profound engineering and scientific achievements of the modern era, opening an entirely new way to observe the cosmos. As established by Albert Einstein's general theory of relativity, gravity is the curvature of space-time. Any massive object creates a distortion, and when massive objects, such as black holes, accelerate rapidly in orbit, they create ripples in this space-time fabric that propagate outward at the speed of light. These ripples are gravitational waves. Unlike light, which is an oscillation in the electromagnetic field, gravitational waves are actual oscillations in the geometry of space-time itself. When a gravitational wave passes through a region of space, it causes a very specific oscillating distortion. It stretches the space along one axis while simultaneously compressing it along the perpendicular axis, and vice versa. This effect is known as quadrupolar strain. The distance between any 2 points in space is momentarily changed as the wave passes. This change, however, is extraordinarily small, which is the key reason these waves took decades to detect. The most powerful gravitational waves detected so far, those originating from the merger of stellar mass black holes, only change the length of an object by a fraction equivalent to 1 part in 10 to the 21st power. To fully grasp the minuscule scale, this is a displacement 1,000 times smaller than the diameter of a proton over a 4-kilometer length. Measuring such a tiny change required the construction of the Laser Interferometer Gravitational Wave Observatory, or LIGO, and its partners, the Virgo detector in Europe and the Kamioka Gravitational Wave Detector in Japan. The fundamental instrument used by these observatories is the Laser Interferometer. The facility consists of 2 massive perpendicular vacuum arms, each measuring 4 kilometers in length. A single laser beam is split, sending two identical beams down each arm, where they reflect off highly specialized, suspended mirrors and return to a central detector. The beams are precisely timed so that, in the absence of a gravitational wave, they recombine in a state of destructive interference, resulting in no light reaching the final sensor. When a gravitational wave passes, it momentarily changes the length of one 4-kilometer arm relative to the other by that incredibly small amount. This minuscule differential change means the two returning laser beams are now slightly out of phase. The interference becomes momentarily constructive, allowing a tiny, measurable flash of light to reach the photodetector. This faint flicker is the direct signature of a passing gravitational wave. To isolate this minute cosmic signal from all sources of terrestrial noise, from natural seismic rumblings and human activity to thermal and quantum motion, the detectors are marvels of engineering. The mirrors are suspended on complex seismic isolation systems, and the entire apparatus is housed in a high-quality vacuum. Furthermore, the requirement for absolute confirmation necessitates multiple detectors separated by vast distances. LIGO has 2 sites in the United States, separated by 3,000 kilometers. The signal from a black hole merger must be recorded at both sites, arriving at slightly different times due to the time it takes the wave to travel between them. Comparing these arrival times confirms that the source is truly cosmic and allows scientists to triangulate the exact region in the sky from which the gravitational wave originated. The gravitational wave signal itself is an acoustic record of the entire merger history. The initial low-frequency portion corresponds to the slow, billion-year inspiral. The rapid increase in frequency and amplitude is the chirp, corresponding to the violent relativistic dance and maximum energy release. The final, rapidly decaying high-frequency signal is the ring-down, confirming the perfect stable geometry of the final black hole remnant. The detection of the first gravitational wave event in 2015 definitively validated Einstein's long-standing prediction and inaugurated the new field of gravitational wave astronomy. This new form of astronomy provides the only direct way to observe the collisions of black holes and neutron stars, opening up an invisible universe previously accessible only through mathematical theory. The future of this field includes the planned laser interferometer space antenna in space, which will use arms millions of kilometers long to detect the much lower frequency waves from supermassive black hole mergers, ensuring that we continue to listen to this invisible, powerful symphony for decades to come. Our final section shifts the focus from the stellar mass collisions we have detailed to the far grander scale of supermassive black hole mergers, before settling on the ultimate, inevitable state of cosmic rest that awaits all such gravitational remnants. Supermassive black holes anchor the centers of nearly all major galaxies, possessing masses ranging from hundreds of thousands to billions of times the mass of our Sun. Their mergers are 1,000 times slower, billions of times more massive, and fundamentally different in their observational signatures compared to their smaller cousins. The catalyst for a supermassive collision is typically the merger of their entire host galaxies. As two galaxies collide and gradually coalesce over millions of years, their central supermassive black holes spiral inward toward the new galactic core. This inward motion is driven by dynamical friction, where the black holes transfer orbital energy to the surrounding dense field of stars and gas. Eventually, they form a supermassive black hole binary, locked in an orbit that is still vast, spanning light years of distance. The primary difference from the stellar mass events lies in the resulting gravitational wave frequency. Because the masses are so enormous, the orbital periods during the inspiral are incredibly long, often lasting years or decades even at close separation. This immense scale generates extremely low-frequency gravitational waves down in the nanohertz range, corresponding to wavelengths that can span light years. Terrestrial detectors are simply too small to measure these long wavelength ripples. To detect these waves, scientists employ pulsar timing arrays. These arrays use precisely timed millisecond pulsars, rapidly spinning neutron stars, scattered across the Milky Way as a kind of vast, galaxy-sized gravitational wave antenna. The passing low-frequency gravitational wave subtly stretches and squeezes the space-time between Earth and the pulsars, causing minute, correlated advances or delays in the arrival time of the pulsar's radio wave pulses. By measuring these minute variations, scientists can infer the presence of the stochastic gravitational wave background generated by the multitude of supermassive black hole binaries across the entire universe. A crucial distinction is the environment. Unlike the relatively clean vacuum of stellar mass mergers, supermassive black holes are always surrounded by a dense core of stars and vast, swirling accretion disks of gas and dust. As the supermassive black holes orbit, they violently stir this gas, heating it to immense temperatures and causing it to emit copious amounts of light across the electromagnetic spectrum, creating active galactic nuclei and potentially powerful jets. This means that supermassive black hole mergers are the universe's greatest example of multi-messenger events, detectable through both their gravitational waves and their resulting electromagnetic radiation. Astronomers anticipate observing flares, jets, and increased luminosity from the galactic core, synchronized with the detection of their low-frequency gravitational waves. This combination provides an unprecedented opportunity to link the invisible dynamics of space-time directly to luminous activity in the universe. Regardless of whether the final black hole is stellar mass or supermassive, the ultimate result is the same: a final state of ultimate cosmic rest. Once the violent ring-down phase is complete, the newly formed, heavier black hole stabilizes. It becomes a perfect, featureless, and stable object, a Kerr black hole defined only by its enormous final mass and its high inherited spin. This new object then enters an epoch of profound cosmic slumber that is nearly eternal. It will continue to increase its mass slowly by capturing stray stars or gas, but its life is essentially quiescent. Theoretically, over incomprehensibly vast stretches of time, the black hole will slowly lose mass by emitting Hawking radiation. However, the timescale for the complete evaporation of a supermassive black hole is estimated to be 10 to the 100 years or more, a span of time that utterly dwarfs the current age of the universe. For all practical purposes, the single black hole that results from the collision has achieved a state of permanent rest. It is a monument to the universe's ability to convert the most explosive, asymmetric forces into the most stable, symmetric, and long-lived structures. The noise of the merger has given way to a silence that lasts for eons, where the black hole is merely a static, powerful point in the deep, cold fabric of the far future universe. If you found this exploration into the violent beauty and enduring stillness of the cosmos compelling, please consider liking this video and subscribing to the Restily channel for more insights into the science of the universe. Sweet dreams.